Hi, Assalamualaikum. My name is Muhammad Farhan Yusuf. My matrix number is CE190029. Today, I will continue to explain the PBL2 introduction. So, the process of embedding digital information signal into the amplitude phase or frequency of the transmitted signal is known as a digital modulation. The encoding technique has impact on the transmitted signal's bandwidth and robustness to channel in degradation. In general, a modulation technique it creates many bits into a single symbol, and the symbol transmission rate determines the transmitted signal bandwidth. Because the symbol rate determines the signal bandwidth, having a high number of bits per symbol results in a higher data rate for a given signal bandwidth. So the number two is the transmission of the discretely varying signal between two values of physical quantity, one representing the binary number 0 and the other representing 1. So number three is a digital signal is transferred at one bit at a time on a serial transmission line. Analog transmission is the polar opposite of digital transmission, in which data is conveyed as a continually varying amount. An analog to digital converter is ADC can convert an analog signal to a digital signal, and a digital to analog converter can convert digital signal to analog signal DAC. So that's all for the introduction. Continue to the project background. So the project background that the pulse code modulator circuit digitize an analog signal, codes and samples it, and then sends it as an analog signal. To obtain the original signal, the same process is done in reverse. However, several critical parameters must be met during the encoding and decoding process, such as sampling frequency, quantization, interval voltage range, and permissible amplitude modulation in a specific range. And this simulation is given 4 parts of experiment, which have part A, B, C, and D. Each part have its own requirement to running the simulation. Depends on the information such as two simulation with bit 4 and 8 is running and recorded to the result on the waveform and explain the waveform. Moreover, as the instruction given to explain what happened in this simulation if the amplitude of MT is changed. After that, record the display result and explain it in the video presentation. Lastly, it has to be done to decide which of suggesting what method or way to get a result of the MT is similar, such as maybe can edit the block diagram, or we can set up the block diagram differently in order to answer the instruction given. So let's continue to the filler table. So this is the filler table that we used. So number one is analyze the challenge of analog to digital conversion and in digital signal transmission using the pulse code modulation PCM approach. This is the number one fact, and the idea is solid understanding of PCM, analog to digital conversion, and digital signal transmission. What are the learning issue? How to examine the PCM? So the action that we have to analyze the PCM output with the MATLAB software and display the waveform of the PCM output with an oscilloscope display in MATLAB. So number two is a pulse. The facts number two is a pulse code modulator output is a series of binary digits. The idea is it is necessary to transform the quantized signal into binary codes. And the learning issue is what is the best way to convert the quantized signal to binary codes. So action is by using the encoder. Number three is the pulse code modulator PCM circuit digitize codes and samples an analog signal. So the idea is you could use an analog device that samples the voltage of a continually fluctuating analog signal and keeps it steady level for a set amount of time. Learning issue: what are the steps for coding and sampling an analog device? And the action is you use sample and hold. And facts number 4. To obtain the original message signal, the signal is sent in a coded format that it must be decoded at the receiver. So the idea is to replicate the original signal. The pulse coded waveform must be decoded. How do you decode a waveform that has been pulse coded? action is by using the decoder. So that's all for me. Thank you.
Okay, hi, my name is Amir Ali bin Shariman. My metric number is CE190028. So, in this presentation, where we present about the simulation for part A. So, this is a simulating circuit for 4-bit encoded PCM data. So, the sampling frequency in this part A has been set to 200 Hz, which satisfies the criteria set by this project, which is use 2 FM for the sampling frequency in scenario 1 and scenario 2, as well the criteria by this project. So which will generate the PCM data at 200 Hz and 4 bit per sample. So after done assemble all this, we can run to get the signal waveform. Okay, so this is the waveform that we obtain from the scope for 4-bit PCM simulation, where the first waveform is represented as an input signal, which has been set to 5 peak amplitude based on the given signal in the project guideline. So for the second waveform, where is the represent the output signal, which is set to mt equal to 5 sin to pi times 100t. Okay, for the third waveform is the waveform that sample signal we also peak at 5. We can see that the waveform has been distorted significantly, and that the amplitude of the signal have increased after we have quantized the signal. And lastly is the encoded signal, which has been encoded in 4-bit PCM data format. So next, okay, this is the waveform of the encoded signal. Okay, so this waveform show the encoded signal bit, with the first bit is the first row is a 1 bit, the second is 2 bit, 3 bit, and 4 bit. As we can see that each waveform has a unique interval between them. This interval is caused by each bit binary phase shift. Okay, so lastly, this is a waveform for decoded signal for 4-bit data. Okay, as you can see that decoded signal has lost some the amplitude signal from the original input signal, but the frequency is remain at the same level as the original input signal. The nature of the encoding and decoding process will result some amplitude losses as the waveform is transformed from the digital to analog, but the frequency will be remain original value due to design to operate. Okay, next, this is the simulating circuit for 8-bit encoded PCM data. As the scenario 1, the sampling frequency fs in scenario 2 was 200 Hz, and this met the criteria also that set by project, which is used 2 FM for the sampling frequency. So this is show the circuit that we're using for the part A, which we able to handle the PCM data for at 200 Hz and 8-bit encoded. So when the tools and material has been assembled, we can run the program to get the signal waveform. Okay, so this is the waveform that we obtained from the scope for 8-bit simulation. Sorry. Okay, so the circuit parameter is similar to those used in the 4-bit simulation circuit. The waveform that obtained from the scope for the 8-bit PCM simulation are shown in this signal. The first waveform will represent as the input signal, which has been set to peak of peak amplitude of 5 based on the signal specified in the project guideline, which is mt is equal to 5 sin 2 pi times theta. So following that, the second waveform is a sample signal, which is also peak at 5 amplitude of 5. And then for the third one is the quantized signal. As can be seen, that waveform has been significantly distorted, result in the signal which the higher amplitude. And finally, this is the encoded signal, which is 8-bit data. Okay. Okay, next, this is the waveform for 8-bit encoded data. Okay, so this waveform show the waveform of the encoded signal bits, which range from 1 until 8 bits. As we can see that each waveform has a unique interval between them. This interval is caused by each bit binary phase shift. And then the last scope. So this is a waveform of decoded signal for 8-bit data. So the waveform of the decoded signal for 8-bit data is can be represented like this signal. The decoded signal waveform has lost some of the original input signal amplitude signal, but it's remain in original frequency. This is again due to nature of the encoding and decoding processes, which introduce some amplitude loss as the waveform is converted from digital to analog, but retain the original frequency for us. When we compare the waveform of the decoded signal for 4-bit and 8-bit PCM data, we can see that the 8-bit decoded waveform has a greater amplitude than the 4-bit decoded waveform. We can conclude that the more bit encoded in PCM data, the closer the final signal waveform is to the input signal waveform, as it maintains a higher amplitude. So that's all for part A. Thank you.
Okay, Assalamualaikum and good morning. My name is Imran bin Muhammad Ghazali, metric number CE190118, and for this PBL task 2, I'm going to explain part B, which is the sampling for MT is more than required according to Nyquist, and our group are going to define our own value, and that value is more than 2 FM. And we are going to have scenario 3 and 4. Scenario 3, which is n bits encoded PCM data is equal to 4, and for scenario 4, n bits encoded PCM data is equal to 8. Okay, this is the circuit for part B. And okay, we have decided to use the value of the sampling frequency is 400 so here, and the sine wave is the same, with amplitude 5, and the frequency is 100. Okay, then the bit here is 4, and we're going to see the result. Okay, from the scope, and we can get the result here. This is our 4-bit result for 400 sample frequency, and this is the input signal. This one is the sampled signal, quantized signal, and lastly is the encoded signal. Okay, then what we have here is the 4-bit encoded signal, and we can see this is from the first bit, second bit, third bit, and fourth bit. Okay, lastly is the decoded signal. Okay, here is the decoded signal that we get. Okay, now we are going to compare it with the 8-bit signal with the sampling frequency is, again, we use 400, and the frequency is same with the given frequency, which is 5 amplitude and 100 frequency. Okay, we're going to run it now. This is the encoder. We use 8-bit one. Okay, this is the scope. This is the input signal, sampled signal, quantized signal, and the encoded signal. Okay, now is for the scope, for the number of bits encoded. Okay, this is first bit, second bit, third bit, fourth bit, 5 bit, 6 bit, 7 bit, and 8 bit of the encoded signal. And let's say this is the final signal, which is the decoded signal. Okay, we can compare a bit here. Okay, this is our 4-bit one, and this is the 8-bit one. We can see here there is not much difference in the signal here. But we can see from the decoded signal, which is this one, and for the 4-bit one, the decoded signal is a bit low from the starting signal, which is 5. But on the 8-bit one, get it a bit higher and closer to 5. Okay, see again, this one is for the 8-bit one, and this one is for the 4-bit one. Here it's about 3.2 here, and for the 8-bit one, we get about 3.5, which is a lot bigger for after the signals have been encoded and decoded back. And we can compute that the 8-bit one have better signal, decoded signal, compared to the 4-bit one. 4-bit one in response to the first signal that we have used. Okay, this is the signal that we have used here, about 5 here. but we have some losses, and from the recorded signal we have the amplitude lessen a bit, but the frequency is still the same. And so we conclude that the number of bits, the more the number of bits, the better the recorded signal, and it's closer to the input signal that we have given. So let's check here, 3.2, and for the 8-bit one, we got about 3.5, which is higher. And that's all for part B. Thank you.
Assalamualaikum. My name is Wendy Afranto. I would like to explain for the part C for this project, which is sampling for M is lower than minimum required according to the news. Okay, from the scenario 5, which is a frequency sample lower than 2 FM. Okay, according for the new case criteria, which is the theoretical sufficient condition to allow an analog signal to be reconstructed completely from the discrete time sample. Okay, following the condition here, which is sampling frequency which is lower than 2 FM, can occur the analog signal now reconstructed completely because they have aliasing in the frequency domain, so the low pass filter unable to pick the analog signal. Right? Okay, this is for the connection for PCM. Right? This is the connection here. Okay, for the sampling frequency here we set for 100 Hz. Okay, which is we like to generate for this PCM. All right. Okay, here we can see the four waveform here. The first waveform here is about the input waveform, which is input signal, which is they have 5 amplitude here, 5p amplitude here, according to the MT is 5 since times 2 pi times 100t. Okay, this is the input signal. Okay, here is the output signal. Secondly, this is the output signal. Okay, this is the sample signal, and lastly is the encoder signal. As we can see here, output signal and sample signal, they have the aliasing here, the waveform. You can see there. It's not, they have distorted. Okay, next is encoded signal here. Right, the first one is first bit, second one is second bit, and third one is third bit, and this one is 4 bit. They have dissimilar waveform here. Okay. Okay, lastly, here is the recorded signal. Okay, as we can see here, they have some missing of amplitude from the input signal here. As we can see, there's here 3 because the original signal which is 5, but the frequency is still visited same from the input signal here. Okay, this is because of the processes for the encoding or decoding signal. Process will occur the sum of missing of amplitude here, but the frequency is still same values from the original because the waveform is transformed from digital to analog. Okay, all right, that's all for the part C. Okay, thank you very much.
Assalamualaikum. My name is Muhammad Afiq Izzuddin bin Shahril. My matrix number is CE190132. Okay, so today I will explain a little bit about part D. Okay, so for part D, we need to initial setting in part B are remains. So we just change the VM. Okay, so this is the step size. Okay, so this is the waveform obtained from scope for 4-bit PCM simulation, and this one is for VM15, and this is waveform of the 4-bit encode data. and this one is for waveform of the decode signal for 4-bit data, and this one is waveform obtained from code for 8-bit PCM simulation. So this one we use the 4-bit, and this one we use 8-bit. Okay, so next is a waveform of the 8-bit encode data, and this is a waveform of the decode signal for 8-bit data. Okay, so next is for VM 0.5, and this is the step size. Okay, so the first waveform is a waveform obtained from scope for 4-bit PCM simulation with VM 0.5, and this is a waveform of the 4-bit encode data. So next is a waveform of the decode signal for 4-bit data, and waveform obtained from scope for 8-bit. So after we use 4-bit, we change to the 8-bit simulation. Okay, so waveform of the 8-bit encode data, and the last one is a waveform of the decode signal for 8-bit data. Okay, so for VM 0.5, step size decrease and quantization error of step size also will be decreased. Hence, the accuracy of shape of the signal at OP increase. So signal become smooth. For VM15, step size increase and the quantization error of the size also increase. Hence, error occur more in the recover signal. So the signal is now smooth. Okay, so for part B, okay, so this is our group suggestion to make sure the resultant recover signal MT is similar to modulating signal MT. Okay, so firstly we add the gain here, which is gain block, and we set to 2 gain. And next we change the analog filter design passband edge frequency to 2/100 here. So the waveform slightly similar. Okay, so that's all from me. Thank you.